Hello, everybody, and welcome to today's presentation, Mapping Data Flows Across Apps, Microservices, and APIs, brought to you by Shift Left. I'd like to introduce you to our presenter, Ethan Lighthouse. Ethan is a passionate product design leader who specializes in data visualization and enterprise software. With a hybrid background in software development and design, he especially enjoys bridging code with design when solving customer needs by building state-of-the-art product experiences. Ethan was previously head of product design at New Relic, where he had the opportunity to build and manage a team of talented designers, define design vision, and work closely with other executives in helping shape company strategy.
Great, thank you very much, Billy. Good morning, good afternoon, or good night, depending on where you are. As Billy mentioned, I'm Eitan. I'm head of product design at Shift Left, and today I'm going to cover a few topics with you. I'm going to start by just getting into some of the challenges around mapping sensitive data and why it's getting difficult. I'm going to cover a few common leakage scenarios that continue to plague modern software companies today. And then I'll describe an approach that we invented about mapping sensitive data flows using semantic graphing. And then after that, I'll get into a quick demo of the Shift Left experience so you can kind of get a feel for how what it's like to interact with the Shift Left product in the context of sensitive data. And then I'll cover any questions, which, as Billy pointed out, you can paste into the GoToMeeting system. Oh yes, that's right. So Andrew, our head of marketing, forced me to put this slide in. We're very proud at Shift Left that we've won several awards recently. One I'll mention most recently was the RSA Innovation Sandbox. We were one of the 10 finalists. That was a great honor to be recognized in that event. So I probably don't surprise anyone by saying that in today's modern software company, tremendous amounts of sensitive customer information are being stored. And that information is essentially one of the most valuable assets of a modern company. And mapping that sensitive information is getting much more difficult. One reason is we're seeing faster release cycles. These are modern dev practices where teams are deploying once a day, even multiple times a day, which means there's much less time to understand code and what it's doing. We're seeing modern architectures like microservices, and microservices, in a technical sense, silo the software and therefore spreads out the risk in terms of what pieces of software are doing what with customer information. And in addition to that, we're seeing a human siloing. So the teams responsible for these microservices are also spread apart, which makes it hard to form a unified understanding of what your software is doing with sensitive information. We're seeing increased usage of open source libraries and dependencies and APIs, which adds to the complexity and also increases that risk that external leakages could happen. And finally, as many of us know, there's more stringent regulations being imposed, abroad and locally in the United States and Europe that force us to really classify more things as sensitive, and the onus is on the companies to really manage that, and it can be very difficult to achieve in a sort of automated way. And so if we consider a typical architecture at a company, you've got a series of microservices that are communicating with each other and passing sensitive data between the services. And this might be in a data center or the cloud or a hybrid environment. And then that information is also typically being stored in databases. Some of those databases are in the cloud as well, like S3 storage. And in some cases, of course, you're sending that information back to the web. If this is a web application, then your customers are seeing this sensitive information on their browsers. In addition to that, of course, there are logging facilities, some like Splunk, where you can actually log off premise if you want to. And we've seen plenty of high-profile critical data leaks that have happened in the industry. So one great example, I think it was about a year ago, Twitter famously logged millions of Twitter user login and passwords to a local file. And that was, supposed to be harmless debug code that a developer had likely left in their software, and then that debug code was executing in production and logging those records. So in addition to that, we see common situations where there's a public GitHub repository, and you might inadvertently, in your source code, leave in a sensitive access key in that repo. And in the case, I believe, of Uber, a key was found in a public repo that allowed an attacker to break inside Uber and extract out millions of driver records. And so that was a big data breach. Another example can be any API you're using. I don't have an industry example right now, but many software solutions rely on tracking customers using a third-party API like Salesforce. You can very easily accidentally add an attribute that is saved into Salesforce that is considered PII, or sensitive personal information. So these are some heavy considerations that burden modern software companies. And so one approach that Shift Left has invented is to graph all information flows in software automatically, and we're calling this the code property graph. You can think of the graph as an assembly of information flows, thousands of information flows. Those information flows represent how data passes through your application logic, how that data passes through open source dependencies and web frameworks involved in I/O if it's a web application, and information flows that also interact with the low-level virtual machine or the low-level system calls, like saving a file, for example. And we call it a semantic graph because we use natural language processing to understand what kind of information, I should say, participates in those flows. And I'll get into more of that in a moment here. So let's consider one data flow. This is an example of an imaginary data flow where each of these cards is essentially a function call. And all data flows start with some triggering function or triggering method that initiates the flow. So if this is a web application, a trigger could be the controller action, so the URL routing system will initiate that. And then a variety of transformation functions might happen that touch the sensitive data in some way. And then finally, the flow terminates with a saving function, which is saving that data to a data sync of some sort. So that could be saving information to a cloud API in the cloud. It could be saving it to a local file or a database. And so if we look at the beginning of this flow, you'll see the first transform function in this particular example is actually responsible for querying the data. This is where the data comes to life, where it's making a database call, and you'll see just above it class person, which is the variable, if you will, that is being initialized at that first transform. And this is where the semantic understanding comes in. The natural language processing that we use reads these variable names like person and automatically catalogs it as, in this case, PII. And this allows us to very, very quickly look through these data flows to determine which ones are touching sensitive data and what kind of sensitive data it is. And then other transform functions are either ushering that data along to the end of the flow, or those transform functions are actually transforming or modifying the information in some way. And so we can look at these transforms to determine whether on its way to the data sync, a piece of data, or in this case, this variable, is being encrypted. In this case, you'll see a little example saying encryption. And so that allows us to understand whether the sensitive data flow is handling the data flow is handling the sensitive data safely or unsafely, or whether this represents a data leak based on what the saving function is doing with it. And all of this, of course, can be driven by policy. So if you imagine a queryable graph database of thousands of these information flows representing one application, then we can query that to uncover kind of what we call the security DNA. We can query that graph database to understand all entry points of information into the application and all exit points. And of course, we can determine based on policy what we'd consider to be a data leak in that case, and uncover multiple data leaks potentially. One of the unique advantages of analyzing an application this way is we can also use this approach to uncover vulnerabilities. The reason why that works is because ultimately a vulnerability is an input that an attacker can leverage that on output can cause some sort of damage or cause data exfiltration. And so in a very similar manner, we find vulnerabilities in custom code, but we can also find vulnerabilities in dependencies because, as I sort of described earlier, the way that these flows are assembled, we look at the flow right into the library that is also performing some sort of I/O. So we can know not just, hey, you're using a vulnerable version of, I'll make something up, the Spring, which is a web framework in Java, but we know that the way you're using it allows an attacker to leverage an injection attack of some sort, let's say. So now I'm going to get into a quick demo and show you in the shift left experience what it's like to interact with this queryable graph database in the context of monitoring security for an application. So let me back out of here. And I want to make sure I open the right thing. Okay. Great. So right now, I've got the main shift left dashboard open here, and this is an application that we're monitoring with shift left and analyzing with shift left. So I'll explain that really quickly. The shift left solution is a hybridized approach. So I've spent most of this webinar describing the analysis of static code to assemble that code property graph that allows us to uncover vulnerabilities and sensitive data flows. In addition to that, the shift left solution has a runtime agent that runs with the application, and that agent is automatically configured to protect the software in runtime based on the analysis that the static analyzer produces. And so as I walk through this experience, I just want you to consider that all of the views that you're going to see are actually merging those two data sets together. So you're seeing insights from the code property graph or the analysis. Also, you're seeing runtime context sort of overlaid on that. So you have an understanding of whether things are being executed in runtime or not. So I'll show you what that means. So as I click into this application, the first thing we encounter here is a dashboard listing out vulnerabilities for every version of your software. So this is something I'd like to emphasize, which is, what I said earlier is that it's not just the challenge of, architecture and understanding information flow that burdens us, but the fact that modern software developers are deploying very quickly in their CI/CD process. The analysis on our end can produce a code property graph within minutes, whereas often other analysis tools can take quite a bit longer. And so what this histogram is showing is actually every version of this software that's been analyzed. We can go back historically and look at all of the findings in the table below. Full screen this. So we can look at these findings in the table below. I'm going to skip vulnerabilities for a moment because I'd like to focus on the sensitive data use case for now. So I'm going to go over to the data flows experience. And what this experience is doing is summarizing all information flow in the application and flagging things that are potential data leaks. So let me just walk you through some of these page elements. The first thing you'll see up here is a throughput chart. So this throughput chart is just showing you regular traffic. If an alert fired, you would see vertical lines in time, signifying that an alert is triggered. That's a security incident of some sort. And I've just triggered a little bit of traffic on this application just now. And so the bottom part of the screen is really split between these two wings. On the left side, we have what we're calling triggers. So I sort of explained what triggers are earlier when covering a data flow. In this case, because this is a web application, these triggers that initiate all data flows are labeled by the URL routes because the analyzer does some extra dirty work to associate URL routes with the actual functions. But if we didn't know the routes, these would look like functions. On the right-hand side, we have data destinations. That's the section headers. So HTTP is a data destination because it's talking back to the web. You'll see over here the logging system is a data destination. And then other data destinations as I continue to scroll. And we're seeing a summary of sensitive data categories like payment data and PII being sent out to these data syncs, and they're marked, or the colored bars, I should say, indicate how much runtime activity is causing these flows to get executed. So one way that you can kind of prioritize what you focus on is, as many of you know, there's a lot of logic in software. Some of it's legacy logic that never executes in production, or debug logic. And so it's hard to know when you look at code what will actually happen in runtime. And so here we can definitively say, well, I might prioritize some of these items over these ones because it doesn't seem like these ones are really executing in runtime. So I'm going to focus on one particular data leak, I guess, in my opinion, which is here we're seeing data classified as payment data being saved out to the logging system. So let me dig into this. So now I've filtered the whole experience, and I'm seeing at the top these two purple cards indicating I filtered by log as the data sync and payment data as the category of information. And now we'll see the triggers just represent the routes into the application that caused this data leak to happen. And on the right-hand side, I can see individual Java variable names here. So this happens to be a Java app, and you'll see it framed as in this case, an account model, and the account is the variable name as well. And we're seeing that this is truly happening in runtime. So the blue bar is showing us that activity is truly triggering this information flow. And we'll see stuff down here that isn't being triggered in runtime. So I'm going to prioritize focusing on account and drill into this. And now what we're looking at is the deepest level of depth that you can look at in this UI, which is down to a code level, a line of code level visibility into what this data flow is doing. And so I'll just quickly explain this. This is a very short data flow where there's only one step in the middle between the triggering function and the saving function. On the triggering function, this just looks like a regular controller action to me from a web framework that is receiving an account parameter. And there is one transform which looks like it's just ushering it through to a logging statement here. So we're using a common logger library with an info call to hand it a parameter, but that parameter, called param1, is just the default way of describing a parameter, is that account variable. And so at this point, we've got this unprecedented code level understanding of how this data leak is possible. And this is when I'd likely get a developer involved to go resolve this issue. So when I started this exploration into the security of an application, I started at a very high level view, a bird's eye level view, where I can see all activity on the application, all information that application touches and where it goes, and finally, very quickly get to this depth where I can show exactly where in the software a developer may want to fix this issue. So pretty cool. The last thing I'll say on this particular dashboard is the middle part summarizes not just findings related to sensitive data exposures, but also all other kinds of vulnerabilities. So here you'll have a column that says, 89 injection vulnerabilities are detected in code. And we see out of those 89 locations in code where injection is possible, 2 of them are actually doing something in runtime or being attacked in runtime. So again, this is an effort in prioritization. And so I'm going to go to the vulnerabilities dashboard and see if I can find one of those. So I'm going to, so we're already on the latest release here. So I don't need to look at a historical version of the analysis that happened today. And I'm going to filter by type. I believe it was a form of injection. Session injection, let's say. Okay, that's not a red one, but it'll still work as an example. Actually, let's just go with cross-site scripting. And so what we see here is a list of vulnerabilities filtered by what I'm interested in. And I can sort by calls or security events. So these 3 columns are runtime metrics overlaid on findings that came out of code analysis. So we'll see here, okay, clearly these other ones aren't really happening in runtime, but this one is. 118 calls, 118 of them are security events. So that means it's more than just regular traffic. We've detected something isn't right here. So I'm going to open up the vulnerability, and I can actually look at the data flow. This is a later version of our data flow viewer, but it's the same thing. It's a triggering function. There are transformations it goes through, and then there's the final call that may be saving it to a data sync or something. And so I can leverage a Jira integration here to actually assign this into Jira. And now this vulnerability in the dashboard, its status will be synchronized to the status inside Jira as a developer investigates this. So I think a pretty cool collaboration between app security and engineering. So just for the last few moments of this demo, and I want to remind you that we can take questions, so you feel free to, if you have them, put them in. You probably already have, I just haven't looked. But I spent most of this time exploring the sensitive data analysis within a single application. And as many of you know, and what I said earlier is microservice architecture is a real strain in understanding it. And so in order to understand at an organization level what you're doing with information, it's often not enough to look at one application at a time. And so one experience that I'm very excited about that we're working on is, let me just get out of this, is our topology view. So I'm going through this this mock-up experience to show it to you. If I, instead of looking at things as discrete applications, I look at it as a map. And leveraging runtime, we can track how services are communicating with each other as well as data syncs, and then understand at this high level what sensitive information is doing across my entire architecture. So in this case, you'll see a grouped bunch of services under this folder called AWS East, but we also pulled out a few services, one called Storefront UI and Account Service, which is talking to some data syncs. And we're seeing some issue here. And what I can do is open up the overlay, the dimension overlay for sensitive data. And you'll notice as I hover over these data categories like medical and PII, you can see that there's a line highlighting inside the topology view. So now I can, at a glance, see how, for example, PII flows through almost everything on my service architecture. But if I hover over authentication, that takes a more discrete pathway between Storefront UI and Account Service. So this is a pretty powerful way to, at a glance, understand information flow across your entire architecture. So super excited about this feature that we're working on. So that concludes the demo. And let me return to the presentation. So before I take questions, I just want to mention to the audience that we're offering a free data leakage assessment. And so if you please get in touch with us, we have a URL there, and we'll show it again while I'm taking questions. But if anyone's interested, reach out, and we will provide a free analysis of one application and provide a GDPR report or a sensitive data assessment report, where you can get an exhaustive list of all of the information flows within your application, along with that semantic flagging, if you will, of the sensitive data. So that would be the sign up URL again is down there at the bottom. All right, I'm going to go look into the questions now. Sorry, I'm going to read them before I. So here's a question. How much overhead does shift left add to the overall throughput? So I assume, of course, that's about the runtime agent. So on the data analysis side, there would be a little bit of time to scan the code, but it's fairly quick. On the runtime side, this is a really important question because often, RASP agents and other types of runtime instrumentation can add significant overhead. This is something that we were very concerned about in the very early days of designing the runtime agent. And so the quick answer is there's very, very little overhead if you compare it to other solutions that you may be used to, including APM and RASP. And the reason why the overhead is so low, or the micro agent, I should say, is extremely lightweight, is because of how it instruments. Most solutions, and RASP and APM both fall into this camp, are burdened with having to instrument everything, all pathways, in order to inspect and look for attacks. Of course, in the case, APM does not look for attacks, but so it's applying complex rules to look for attacks in runtime almost everywhere in the application, and that does introduce overhead. But in the case of shift left's agent, it only monitors for attack where vulnerabilities are known. So in other words, a RASP agent, which is dynamically sort of analyzing as runtime is happening, if there are 100 places where SQL calls are happening, it has to watch all 100 and monitor for the attack patterns for all 100. In the case of the shift left agent, if only 5 of those are actually vulnerable, because in the analysis we know that it was vulnerable, the analyzer, the code analyzer, auto configures the agent to only instrument those 5 locations. So that's quite a bit less overhead. I'm reading some more here. One question: does it run on existing code base? I'm not entirely sure what you mean by that question. If what you mean is like, do you have to write, like, do you have to analyze code as you're writing it, as opposed to can you take like a legacy code base and analyze it? The answer is it doesn't matter. So yes, you can take a 500,000 line legacy piece of software and analyze that. If I didn't understand your question correctly, feel free to ask again. Yeah, so there's another question asking about a specific code analysis tool versus ours. I don't want to publicly talk about a competitor, but I will talk about how we differentiate from almost all other code analysis tools. The primary struggle with using most code analysis tools out there in the market is they tend to be extremely slow. What we found when we looked at them was, especially for large code bases, they could often take hours and sometimes days to do an analysis, which means you're interpreting those results completely outside of completely outside of the engineering CI/CD process, because it's just too slow to meaningfully incorporate into engineering cycles, which means it's almost always out of date as a result of that. So very hard to take action on. The other issue is they tend to have a lot of false positives. So, of course, you might get 1,000 results out of your code analysis, and it will be nearly impossible for you to know that out of those 1,000, there are these 10 that you are critically vulnerable to. So the false positive problem is very real. And then the third one that we found was that the most code analysis tools don't have a complete understanding of the application context. So what I mean by that is they often don't analyze deep into the dependencies to interpret issues both in custom code and those open source dependencies or libraries. And furthermore, they're not doing the semantic understanding. So you're not going to understand, beyond vulnerabilities, you're not going to understand much about sensitive data from popular code analysis tools. The way that I want to address the one about the first thing about the speed. So the shift left analyzer, when we developed it with a code property graph as that sort of engine at the base of it, we developed that from the ground up to be extremely fast, because we knew that speed and efficiency and being able to have it integrated into CI/CD is priority number one. So ours runs within minutes as opposed to hours and days. And then for the false positives problem, we do have more context. So we do claim to have lower false positives and higher accuracy. But in addition to that, because shift left is a hybridized solution that where runtime works closely with code analysis, they feed each other. So as I mentioned, code analysis helps auto-configure runtime, but runtime also helps you prioritize code analysis. So even if you have, let's say 100 things that you have detected from code analysis with shift left, we can tell you that 4 of them are executing in runtime and the rest aren't. And so that's one way you can prioritize and not worry as much about false positives, and knowing that the runtime agent will automatically protect those other 96 vulnerabilities. Let's see here. Right, okay, so this is a good one. Can I use this to follow the usage of particular data elements throughout my API catalog? And then the question in that question is also, is this dependent on the data element name being consistent? So the API catalog question is ideally yes. So this approach will allow you to understand how information is used across services talking to each other in an API. If there is an API with an external service, obviously we're not monitoring the external service. If you're saving data, to some cloud vendor like Splunk, I know Splunk can also be on-prem, but we can at least know that that's going out onto that data sink, and so you would be aware of that. In the case of the consistency of naming, that is a factor. So there is a default policy that you get out of the box with the shift left solution. So as soon as you run analysis, the semantic understanding of variables will come up right away, and it uses all sorts of methods to automatically catalog something. So even if I guess there's 2 concerns there. One is, let's say you've got a person object used by these services over there, but then it gets renamed a customer, by a bunch of other services, but it's effectively the same information in your architecture. The fact is it'll all be cataloged as PII anyways, likely. So you can still kind of glanceably track all that stuff with inconsistencies. That said, the policy that drives the semantic understanding is augmentable. So you can introduce your own variable names into that semantic understanding, that policy, I should say, so that other things get cataloged that may be weird variable names that just don't get picked up by anything. So yeah, that can be customizable. In terms of consistency, the only recommendation I would have there is, if you interchange the name customer and the name opportunity or something in your code, and they both mean customer, you would just augment the dictionary to ensure that they both are classified as PII, and then you're good to go. Reading more. Oh, hold on. Okay. Okay, so this is a continuation of the question from earlier, where it was like, how does it run on existing code bases? Does it run on existing code bases? And then the follow-up is, is it an API in your application to send data remotely about your app, or how does shift left analyze all code? So I want to make this super clear. The way the code analysis works is you would integrate a command line tool from shift left into your CI/CD pipeline. So if you use Jenkins, let's say, when you package your application prior to deployment on your Jenkins machine, you have a shift left command line utility that you trigger analysis on your software package. So if it were a Java app, for example, it would analyze the jars on disk. And so those jars usually have the dependencies with them as other jars that are part of that same package. And so yeah, the analysis is a static code analysis. In some cases, it's analyzing the source code itself on disk. This is a very language dependent question. That's all. That's why I'm kind of interchanging changing stuff here, but in the case of Java, it can also analyze the jar directly, the bytecode. So that does not require any instrumentation or shoving anything into a running application to analyze it. So this is all static code analysis. And then the runtime agent, that one is, like I said, configured, and when you do that same Jenkins build, once it goes to production, there is a flag in the case of Java, for example, to use our runtime agent jar, which then runs along with your application, very much the way an APM solution would do it if you're familiar with something like New Relic or AppDynamics. And so that shift left agent jar that then runs with your app is configured based on a local shift left config file, and that file is automatically modified by the code analysis. Hopefully that was pretty clear. Okay, so I'm going to keep going here. Some good questions. Yeah, I think I answered this already. Someone was asking, how does it know what categories are PII or health? Does it know out of the box? How much setup do I need to do? So I kind of addressed that, but I'll just sort of repeat it super quickly. There is an out-of-the-box policy. We found that it does indeed detect in a lot of our customers' applications when they onboard for the first time. Yeah, they get results right away. A lot of sensitive data is picked up by our default policy working with that semantic understanding. But of course, yes, it's augmentable. So I can't make any guarantees, but yes, it does work out of the box. Keep going here. Yeah, so this is a good question. Is shift left effective with monolith apps as opposed to microservice style architectures? Yeah, I've spent a lot of lip service here about microservices because that is a challenge. But yes, absolutely. Shift left can be used perfectly well with a monolith application, a very large code base. And I guess the good news here is because the analyzer is so fast, it shouldn't be prohibitive to have it in your CI/CD and analyze it quickly, even with a monolith application. Yes. Oh yeah, this is a good one. Many of the apps we have, some executors batch jobs running. Can shift left plot out the semantic graph or some sort of workflow visualizations for batch jobs? Yeah, that's a tricky one. It's a really cool question. So in the case of a batch job, first of all, of course, it is dependent on the language. I'll just right now mention that shift left today supports Java and .NET. We're currently working on other languages to be available this year, I believe, namely Node.js and Golang, and of course the list goes on. But those are the priorities. For us, I believe you can use some of our analysis today on C and C++, but I would need to verify that one as well. So in terms of running like batch code or an execution on your disk, like on your file system, excuse me, it's not a web app, so you're running like a cron job that runs a task that does something with sensitive data. You can, in theory, use shift left analysis on that. You may even be able to monitor that as it runs, depending. So yes, the answer is you could see an app card among others that are traditional web apps and go look at sensitive data in there. In the case of the topology view, which is not yet available, that relies on runtime agent protocols that inject into like communication, or if it's HTTP headers, it would inject in there to track the information flow between services or applications. It doesn't have to be only HTTP. There are other tricks you can use, but it's very difficult to tie that programmatically if it's a batch job running on disk that's like picking something out of somewhere. So at worst, in that particular case, you would still have a single app you could visit representing that batch job potentially, and then look at the sensitive data in there. But on the topology view, what we're going to be doing is allowing you to drag in an app and draw custom connections yourself. Those connections aren't derived from the runtime detection. You're drawing that manually onto the existing topology view with that service. And so at a minimum, you could at least make sure that the dashboard reflects reality, that thing is technically doing something with information, so that other people, when they collaborate with you, they see that on the dashboard. So it's not quite as powerful, but there's a flavor of it that you could do. Oh, the Jira integration. Yeah, can I tell a little bit more about the Jira integration? So yeah, I think one of the most common bits of feedback in the early days of Shift Left is they see how aggressively we are kind of like DevSecOps mentality, which signifies this sort of tight collaboration between engineering and AppSec. So we have some basic ability to mark things as fixed or assign to Shift Left users. Obviously, if you're expecting engineering teams to focus on high priority things, then it's nice for them to have it in their own ticketing system. So we chose Jira as our first integration. There'll be more. And how does it work? Well, it's typical. It's typical that other solutions, the way we've chosen to integrate, and I can't tell you like exactly which style of Jira integration it is, but basically you've got to share some Jira credentials in the integration settings area. I'm not going to dig into our UI now to show it to you, but basically there's an integration section in the Shift Left product, and you can choose Jira in there, and then you got to do this two-way you got to do this sort of like two-way thing where you drop in some configurations into Jira and vice versa. I don't even know if it's vice versa, but you drop some configurations into Jira and vice versa, and then from that point on, every time you encounter a vulnerability on the Shift Left dashboard, you click Assign to Jira. It generates the Jira ticket with some default statuses, and you actually also on our dashboard configure the status. So you configure that, like, what does critical mean as a label inside Jira, as a status inside Jira or something. And you can also configure what finished means in Jira on the Shift Left dashboard. So there's a bidirectional synchronization, and you can be precise about when a developer marks this as done, I want that to mean fixed. Or when a developer marks this as I don't care in Jira on the Shift Left dashboard, that will mean ignore in our terminology. Hopefully that answered it. If I didn't cover a specific thing that you want to know about the Jira integration, you feel free to ask again. What other languages are supported for static analysis? Yeah, so I kind of said this earlier. Java.NET right now today, currently working on Node.js and Golang, I believe. We have another product we call Ocular, which is a BizLogic analysis tool. It's more of a command line tool. It allows you to freely explore the CPG as well as uncover business logic vulnerabilities specific to your application. So that's different than the kinds of vulnerabilities I showed you on the dashboard, which are more standard vulnerabilities. And that one, I believe, supports more languages. I think C, C++ in addition to Java. But yeah, I don't know exactly C++. So yeah, I should be careful what I say, I think. But yeah, answers the static analysis question. Another one about languages. Cool, that helped a lot, great. Is .NET Core supported as well? It's very possible. I can't answer definitively. What I would suggest is get in touch with us to ask. I know a little bit more about Java because that's what I used to do when I used to be a developer thousands of years ago. But no, I'm not as familiar with .NET, so I can't speak to the platforms, unfortunately. So yeah, please get in touch to ask that. Just looking for any more. see here. Does the analysis work with HTTPS in addition to HTTP? And what about other protocols? So this will be my last question that I'm going to answer. One interesting challenge with other security tools, in particular in runtime, if they inspect what's going on, in packets, SSL or HTTPS encryption can be a real challenge on the network. It requires you to put the tooling, behind where encryption goes, and that is a configuration headache. The good news with the shift left solution is because the agent instruments automatically and runs inside your application, it's effectively behind that web barrier, that encryption barrier anyway. So it doesn't need to actually care about the fact that it's encrypted once it's web traffic. So that's pretty cool. In terms of other communication protocols, in runtime, other protocols might be supported. I believe, like protocols like XML-RPC also are ways that services can talk to each other. So I believe that is also supported, but I can't speak at length to all the other protocols that the runtime part detects. Cool. Well, I'm going to end it here for the Q&A, but I'd just like to take the opportunity to thank everyone for attending. I hope you found this informative. Again, feel free to get in touch with us directly. We can answer questions outside of this webinar. And if you're getting in touch with us, we can also do the free GDPR report. So that would be very cool. And that's it. Thank you for your time.